Welcome to our very first Calculus 1 video. I hope you're as excited as I am here. We're going to start our very first video by talking about what the precise definition of what a limit is, or kind of what the technical definition of a limit. Our whole first chapter is talking about what is this thing called a limit, and then we're going to actually use that limit to help us build other cool calculus tools like the derivative and like the definite integral. But let's start by talking about limits. Now, one word of warning I'll give here is that this definition is really technical and it looks really complicated. If you're feeling overwhelmed by looking at this definition, it is totally natural. This is not the definition we're going to be using for the majority of this chapter here. We're going to talk about it in this section, and then we'll come up with kind of a more user-friendly definition of what a limit is. So don't worry too much if you're not following along with absolutely everything here. So let's hop right in. It says, suppose that f of x is defined for all x in some open interval containing c except possibly at c. So let's stop right there. C is some x value. And this is a number that I'll pick, right? So I might say, okay, I want to find the limit at x equals 2 or x equals -5 or something like that. And here f of x is our function. We want it to be defined on some interval that contains c except possibly at c. And what that means is the function should exist everywhere except for perhaps at this one particular x value. Let's keep going. It says, we say that the limit as x approaches c of f of x is equal to L. This is the thing that we're trying to define here. So this is the thing that we want to talk about. And the way we would talk about this, we say the limit as x approaches c of f of x is equal to L. Now L, this is the limit. This is oftentimes what we're going to be trying to find. So the majority of this chapter we're trying to find out what is L. L is a y value. In this section, I'm hoping we'll gain a kind of an intuitive sense for what a limit is, but we're actually not so interested in evaluating limits as we are proving them. So I will actually tell you what the limit is. It's your job then to go and actually prove to me that the limit is what I said it was. So we say that the limit as x approaches c of f of x is equal to L if for any real number epsilon greater than 0. So now we start with these Greek letters. Epsilon is, first of all, epsilon greater than 0. Epsilon is a positive number. And what I want you to think about epsilon, this is a small change in y. This is a small set change in y. So this is a number that I will choose at the very beginning of the problem, and it won't change for the rest of our problem. So in most of the problems, we'll use epsilon equals 2 or epsilon equals 1. If you look up other examples online, they might choose epsilons that are even smaller. We might choose epsilon to be 0.1 or 0.001. Generally, it's a very small number, and it represents a change in y. Then there exists a delta greater than 0. So this is a number that you have control over. You don't get to choose what epsilon is, but you do get to choose what delta is. Delta is a small change in x. Small change in x. And you get to go and choose what this number is. That's often the end result of these problems. I'll say, go find a delta that satisfies this criteria. That satisfies then absolute value of f of x minus L is less than epsilon whenever 0 is less than absolute value of x minus c is less than delta. So absolute value, let's just start by talking about that. I think we all know how to find absolute value, right? It takes a number, it makes it non-negative, right? So it's either positive or it's 0. But another way to interpret absolute value is it measures distance, it measures the total distance you are away from a certain point. So I'm actually going to work my way backwards here. When I talk about this guy right here, this really says the distance between some x value and c is less than delta. So you get within 0.00001. Whatever number you say your delta is, you get very close to that c, that x value that we gave at the very beginning of the problem. So if this happens, then it is guaranteed that if you take that number and plug it into your function, so that's what this f of x is right here. If you plug that number into your function, it will be within epsilon units of L. So that means you're very, very close to our limit. And that's really all the limit says. It says, you know what, if you take a number that's very, very close to some x value, so if you pick an x value that's very, very close to 2 and plug it into your function, you're going to get a number that's very, very close to your y value that corresponds to that. So let's draw out what this might look like here, because I think that's the easiest way to understand and get a good representation of what a limit is. And I'm going to start with a linear function here, which I will call f of x. And I'm going to pick some arbitrary x value here. So I might say, okay, my x value is right here. This is x equals c. Now, I'll tell you in this problem that the limit over here, the limit is this guy right here. This is my limit L. So, again, I'll give you epsilon at the very beginning of the problem, and that's a very small change in y. So that's the distance from L. So I'm going to come up with two numbers here. I'm going to say this is L plus epsilon, and this is L minus epsilon. So I'm just moving epsilon units away up and epsilon units away down. So I'm just moving a little bit away from this number L here. So I've created what is called sometimes an epsilon neighborhood. You don't need to know that. That's a fancy math term. But if you want to impress your friends, we have this epsilon neighborhood. You want to kind of land in between L minus epsilon and L plus epsilon. That's our goal for a limit. So what we can do here is we can kind of work our way backwards. We can say, okay, if we take L minus epsilon and L plus epsilon, and we kind of see, okay, what x values do these then correspond to? This is a linear function, so it shouldn't be too bad to come up with here. So let's suppose that these 2 points are exactly the same distance away from C. Perhaps maybe delta units away. So this would be C minus delta right here, and C plus delta right here. So this distance right here is delta, and this distance right here is delta. So what the limit says, and if we've done this correctly, this is what we're saying, is we're saying, okay, we're going to find a delta so that if you choose a number that is within delta units of C, so that means if I choose a number between this point here and this point right here. So if I choose just to pick a number, right, if I just pick this point right here, and I plug that into my function, it's going to land me between L minus epsilon and L plus epsilon. So if I take this number here and I plug this into my function, so right, I plug this into my function and I find the y value that corresponds to it, I'd like to land right in between L minus epsilon and L plus epsilon. And here we go, we have done exactly that. We've landed right between L minus epsilon and L plus epsilon. So your goal here is you need to decide, well, how close do we need to get to C in order to land in between L minus epsilon and L plus epsilon. The functions we'll be working with are relatively simple. We'll be looking at a few graphical examples and a few algebraic examples in the next video if you want to take a look at those. But that's really all this says, is you have to decide how close do we have to be to this x value C if we're going to be very, very close to this number L. So take a look at the next few videos. I think that'll help shore up your understanding of exactly what a limit is, and we'll kind of get to see it in action.